Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the SERDP and ESTCP webinar series. I have the pleasure of facilitating today's event. This webinar focuses on DoD-funded research on advancing innovative membrane technologies for treating complex munitions manufacturing wastewaters. We will have Dr. Brian Chaplin from the University of Illinois, Chicago, and Dr. Paul Hadzinger from Acton, who will be giving two presentations on this topic. Each presentation will be followed by a brief Q&A session, and depending on how we're doing on time, we will conclude the webinar with a longer Q&A session. The next few slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provided to you in your webinar registration confirmation email. If you can download Zoom, you can still view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you have technical difficulties and your screen freezes, just try keying Control and F5 to perform a hard refresh of your screen. And in case of continued technical difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. Another way to follow today's proceeding is to go to the SERDP and ESTCP YouTube channel at the link shown here, as we will be live streaming this webinar. As far as the Q&A periods, note that the broadcast is listen only. You can submit questions by using the Q&A box on your screen. Please do not wait until the Q&A period to get your questions in. We encourage you to submit them well in advance of the Q&A sessions. We ask that when you please submit your question, just add your organization name at the end of your question so that we can identify you during the Q&A sessions. We ask that you please not submit questions in the chat box. The chat box is reserved for comments related to technical difficulties. And with that, I would like to introduce Dr. Andrea Leeson, who is the Executive Director of SERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with SERDP and ESTCP since 2001, and before that, she served as a research leader at the Battelle Memorial Institute, where she conducted scientific research on in situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for both site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, I'm going to turn it over to you.
Thanks so much, Rula, and thank you for everyone who's joined us today to listen to these presentations. Before we jump into the technical presentations, I'd like to give you just a little bit of an overview about who we are to really set the stage for the technical presentations you'll see today. Slide 10. So we are two companion programs. The first is the Strategic Environmental Research and Development Program, or SERDP, and you can see this as a traditional R&D program that is a partnership between the DoD, DOE, and EPA. ESTCP is the companion program to SERDP, which is the Environmental Security Technology Certification Program. And under ESTCP, we demonstrate and validate innovative technologies at military installations. The goal being that the demonstrations will provide the information needed by the DoD and our partners for technology transition and ultimately commercialization or broader adoption of those technologies. Slide 11, please. Really, the entire goal of SERDP and ESTCP is to deliver value to the military installations. We do this through a number of means. One is certainly by enhancing mission readiness. We ensure health and safety through the types of demonstrations and technologies that we develop. We're looking at cost savings by the development of these new technologies, and we're certainly bolstering chemical and material resilience. Slide 12, please. We have 6 program areas that support these DoD priorities. The first 3 shown here are environmental restoration. And while we highlight PFAS in this particular area, we also are looking at other chemicals of concern, including legacy chemicals such as 1,4-dioxane, and we look at some of the military munitions constituents, which is what you'll hear about today. We also work under resource conservation, weapon systems and platforms, slide 13, installation, energy and water, natural hazards adaptation, and munitions response. Slide 14, please. And we really are looking to fund these critical R&D efforts. Over the years, we have funded over $750 million in our R&D portfolio, with over 3,000 different projects funded. We've funded hundreds of different federal, university, and industry entities, and one item that I'm particularly proud of is the partnerships that have been formed between all of these entities, which ultimately result in stronger projects and a stronger ability to meet the DoD mission. If you would like to receive updates about the program, particularly about our funding opportunities or these webinars, you can sign up for our listserv at this link below. Slide 15. For upcoming webinars, we keep an active webpage here that you can go to. It will show not only the upcoming webinars, but it will also show the archived version of all past webinars. So if you've missed something in the past or weren't aware of it, you can go back and listen to the webinars and the Q&A at the links provided there. Slide 16. I'd also like to highlight that SERDP ESTCP, in conjunction with 2 other DoD programs, OECIF and OEPF, we'll be hosting an applied innovation workshop in December in Washington, D.C. This is an amazing opportunity to see a little bit of everything that these 4 programs are funding through various workshops as well as poster sessions. And I encourage you to take a look at the registration site and consider attending. Slide 17. So at this point, I'm going to turn it back to Rula to introduce our first speaker. Thank you.
Thanks, Andrea. It is now my pleasure to introduce our first speaker, Dr. Brian Chaplin, who is a professor as well as director of graduate studies in the Department of Chemical Engineering at the University of Illinois, Chicago. Brian is also the founder of Xivent Research and Innovations, LLC. His research focuses on the development of advanced electrochemical and catalytic processes for water treatment, with a particular emphasis on technologies that enhance water sustainability. Brian has been recognized with several prestigious awards, including the 2015 NSF Foundation NSF Early Career Development Award, the 2019 ESNT Early Career Scientist Award, and the 2018 ESNT Best Paper Award in Environmental Technology. He earned bachelor's and master's degrees in civil engineering from the University of Minnesota and his doctoral degree in environmental engineering from the University of Illinois at Urbana-Champaign. Brian, we're delighted to have you. Please go ahead and get us started.
Okay, thank you very much, Rula, for the introduction, and I want to thank everyone who's joining us today. It's my pleasure to present my SERDP-funded research that's focused on the electrochemical destruction of munition constituents in manufacturing wastewaters. So I'll start with a brief outline. I'm going to start by summarizing the problem statement and then go into a description of our technology, which we call reactive electrochemical membranes. I'll then go over the technical objectives and then summarize some of our key results from the project. And then I'll end with a discussion of conclusions as well as benefits to DoD. So the real issue we're facing here is trying to treat munitions manufacturing wastewaters. And these wastewaters can become complex. They contain various organic contaminants, as well as inorganic oxyanions, such as nitrate and perchlorate. And traditionally, these have been treated by a combination of biological and absorbent-based treatment methods. However, more recently, the legacy munition constituents have been replaced with what what's called insensitive high explosives, or IHEs. And these compounds are more persistent, so they're harder to destroy. They also have a much higher water solubility that make it more difficult to use absorbent-based treatment methods. So to provide a little bit more details about what's in these wastewaters, I want to summarize the primary constituents. So there are the legacy munitions, which are shown in the top of the figure on the right, and these include things such as TNT, RDX, and HMX. These are typically treated, as I mentioned, by biodegradation or carbon absorption. However, these are being replaced by these IHEs, and these compounds are shown on the bottom of the figure. These are compounds such as NTO, DNAN, and NQ. And these compounds are much more stable to heat and shock waves, so that prevents accidental detonation of these compounds during travel and other instances. But when we're looking at wastewater treatment, these are much more water soluble and recalcitrant, so it makes it much more difficult to treat. These wastewaters also contain toxic oxyanions, such as perchlorate, which is used as a propellant, and often nitrate is also present in the wastewater as part of the manufacturing process. These oxyanions are typically treated by biodegradation or ion exchange. So the goal of our project was to develop a destructive treatment strategy that could eliminate all of these compounds that I mentioned on the previous slide. So overall, a very simplified treatment train is shown here where we take this wastewater feed, we send it through a particle filter, and then to our destructive treatment technology. So we're focused on an electrochemical destructive treatment technology to remove all of these compounds. And then depending on the effluent concentrations, there may be the need to do some polishing, such as using GAC columns to remove some of the residuals that were not removed by destructive treatment. So once this is accomplished, then the water can be discharged back into the environment. So to go in a little bit more detail about our technology, we call this reactive electrochemical membranes. So these are conductive membranes that can function both as a membrane and as a reactive surface. And these are nominally made from Ti-407, which is a suboxide of TiO2. And we are really not taking advantage of their size exclusion properties for this project, but more we're taking advantage of the reactivity and also the very high specific surface area that allows us to get high removal rates with only single pass operation. So schematically, I'm showing conceptual operation of this technology for removal of all these compounds I mentioned. So first, the water would go through the anode, and these organic constituents, either the legacy contaminants or the IHEs, would then be oxidized to their mineral products, which would be things such as nitrate, CO2, and water. The water then passes on to the cathode, where we can then reduce the nitrate that's formed on the anode, along with the nitrate that's already present in the wastewater, to nitrogen gas. And then any perchlorate that may be present, we can reduce that to chloride. So conceptually, we can use one electrochemical cell to take care of all of these contaminants that I mentioned. So to go in a little bit more detail about our technology, one of the main innovations is the mode of operation. So traditional electrochemical cells utilize flat two-dimensional electrodes. They're placed relatively close together and water is pumped through them. This mode of operation, known as flow-by mode, creates a very large boundary layer at the electrode surface. So that results in very low mass transport rates. And also because these are just two-dimensional surfaces, they have very low specific surface area. So the consequence of this is that we need many of these electrochemical cells in parallel as well as in series to meet our treatment objective. So what we've done is we've made porous electrodes so we can flow the water through the electrode itself. And this is called flow-through mode operation, highlighted on the bottom of the figure. And we produce these electrodes with about 1 micron pores. So the distance that these contaminants have to travel to get to the pore wall is very short. So that results in very high mass transport rates. And because these are three-dimensional electrodes, we take advantage of all the internal surface area. So we have a very high specific surface area available to us for reaction. And the result of this is we can use fewer electrodes, and we can also get, in some instances, complete contaminant removal in just a single pass through our electrode. So that brings me to the technical objectives of this project. Our first is to develop efficient, robust, and low-cost electrocatalysts for the contaminants that I mentioned. We then optimize the operating conditions to provide cost-effective treatment. And lastly, we performed an initial LCA or life cycle assessment for the REM and compared it to absorbent-based treatment strategies. And this is very important to do this early on because then we can identify areas where we can improve upon and lower the environmental impacts. So I'll start by giving the reactivity of our organic munition constituents. So in the top row of this figure, I'm showing our IHEs, and in the bottom row, I'm showing the legacy of munitions. And so as you can see in these reactions, first I want to mention that these were all done at pH 7 with a flux of 240 LMH. So this stands for liters per meter squared per hour. And this translates to an 11-second reaction time. So the solution spent about 11 seconds inside of our anode. And in all cases here, when we get to about 3 volts or a bit higher, we're able to get complete removal of all the IHEs and also all of our legacy munition constituents. So although removal is very important, we also are very mindful of the products that we form. And so for all of these compounds, we were able to remove them to below our analytical detection limits, which range between about 50 to 170 nanomolar. But what we were really tracking is the nitrogen and where that goes. And so if we get complete oxidation, we should be forming nitrate, with all the nitrogen should be converted to nitrate. So for many of those compounds, that is the case. So for DNAN, and which is shown in the top left here, we're able to achieve stoichiometric concentrations of nitrate. And for a mixture of TNT, RDX, and HMX, which is shown in the bottom right, we oxidize these as a mixture. We also were able to obtain 100% nitrate conversion. We also measured the chemical oxygen demand, and we were able to show that we removed greater than 99% of that. And that's indicative of a mineralization process. So for these compounds, we're very confident that we're completely mineralizing them and we don't have any significant concentrations of byproducts. For NQ, however, that was a little more difficult to treat. We had about a 75% nitrate yield, and results are shown in the top right. And we did see evidence of polymerization, which I'll talk about in just a moment, that affected the performance. And then lastly, NTO, which is shown in the bottom left. We had a mixture of nitrogen products. About 50% of the nitrogen was oxidized to nitrate plus ammonia, and the other 50% to nitrogen, which was assumed based on the mass balance. We did not detect any other nitrogen species in solution. And I should mention that this product distribution is very consistent with other AOPs or advanced oxidation processes for NTO. So as I mentioned, NQ posed some challenges to us in terms of polymerization. So we detected polymerized products on the anode surface. So we wanted to investigate this in more detail and also vary the solution conditions to see how that affect our performance for NQ removal. So we did this experiment with a high concentration of 7 millimolar of NQ at a high potential with the same reaction time of 11 seconds. And so what we saw, which is shown on the top left, is that we had significantly decreased removal over time in all the electrolytes we tested except for sodium chloride. And you can see that the concentrations in the permeate increased over time for the other 3 electrolytes. However, with sodium chloride, chloride is oxidized in our anode to produce chlorine, and chlorine has been shown to be very effective in the oxidation of NQ. So over the 200 minutes of reaction here, at the beginning of the reaction, we had greater than 99.99% removal of NQ. And even after 200 minutes, our removal was at 97%, which indicates that adding the sodium chloride to the solution was able to to minimize the polymerization, and therefore we were able to maintain a longer term performance. The nitrate yield from the sodium chloride electrolyte is shown on the right, and that did decrease over time, but we didn't investigate the reasons for that in detail. So the next thing that we wanted to focus on was the oxidation of more realistic wastewater streams. So we utilize a multi-stage reactor system, which I'm showing schematically here. And I'll go over this briefly. So we have our wastewater solution here. It would be pumped in a cross-flow fashion, much like you would do for membranes, and recirculated through the inside of the membrane. That is pressurized, so the permeate would then come out, and then we would use that permeate and send it through a second stage and also a third stage. So we utilize this system for the oxidation of IMX 101. We were unable to procure a real wastewater, so we made a synthetic wastewater. And IMX 101 is a mixture of NQ, DNAN, and NTO, and I'm showing the feed concentrations in the table below. And we added sodium chloride as well to prevent the polymerization of NQ. So I'll go over the results for each of the compounds. And so I'm just going to highlight the cumulative removal. So after the first stage, we were able to get about 80% removal of NQ, 99% after the second stage, and 99.99% after the third. For DNAN, we had about half of the removal in the first stage, about 94% after the second stage, and 99% after the third. And for NTO, we had almost complete removal after one stage and 99.95% removal after the second stage. And so we did track the nitrate, and that amounted to about 20% of the total yield went to nitrate. We did not detect any other products. So we're hypothesizing that because of the chlorine, that is reacting with some of the amine groups in these compounds, and it's oxidizing to nitrogen instead of nitrate. We also were able to procure an IMX 104 wastewater, and I'd like to thank Paul Hattinger and Mark Fuller from Apton for providing that to us. We did an experiment looking at the destruction of this wastewater. IMX 104 is a combination of NTO, very high concentration, 78 millimolar, DNAN, as well as RDX. And we, instead of doing a three-stage system, we did this at only a one-stage system, but we decreased the flux. So we increased our contact time to about 88 seconds. So longer contact time, but only utilizing one stage. And so first we added 20 millimolar sodium sulfate to the solution to increase the ionic connectivity, which helped our performance. And over the first about 3/4 of an hour, we had very good performance. We had complete removal of all three compounds. But as you can see in the figure in the top left, the RDX concentrations began to increase slightly over time during this reaction. We did look at the nitrogen compound, so we formed a combination of nitrate and ammonia. And when we looked at the COD for select samples, we saw close to 100% removal. And this is primarily attributed to the fact that NTO is making up most of the organic load there, where RDX is just a small fraction of that. So we've seen these kind of results before where with NQ, and that was due to fouling of the electrode surface due to polymerization. So we hypothesized that adding sodium chloride may be able to help us with that deactivation that we observed over time. So we did that. The results are shown in the bottom left, but unfortunately what we see is that although NTO and DNAN are removed effectively, RDX removal was less. And we investigated that in a lot of detail. And what we found out was that RDX reacts primarily with hydroxyl radicals, with a minor contribution for direct oxidation. So adding sodium chloride, the chloride is a good scavenger of hydroxyl radicals, so it does not make them available for RDX reactions anymore. So once again, we did COD removal. That's mainly attributed to the NTO removal. And we looked at the nitrate yield. And in this case, we did not form any ammonia, likely because the chlorine that was generated reacted with that and formed nitrogen gas. So the implications of this research are either we have to use a second stage to try to remove RDX, or we could use just a polishing step because RDX is at a very low concentration relative to the other compounds. It's much has a much lower water solubility, and traditionally it's been treated with absorption. So we could use a GAC absorption at the tail end of our oxidation process. Okay, I want to switch gears slightly here and talk about perchlorate reduction. We did a lot of work on perchlorate reduction as well as nitrate reduction, but due to time constraints, I'm just going to mention just the one result here. And so this was using a rhenium-based catalyst, and we deposited it on an REM cathode. So this is a reduction reaction. And the REM, or excuse me, the rhenium catalyst was developed by our collaborator Jingyong Liu from UC Riverside. And so this is not representing a wastewater, but instead I wanted to highlight some results that we did for spiking perchlorate in groundwater at 1 ppm concentration. And so we applied a cathodic potential of -1 volt and did these experiments at a very similar flux to what I shared with you before. One thing we had to do here was do a reverse polarity treatment because the calcium carbonate present in the groundwater would cause scaling of the cathode. So every 24 hours, we would reverse the polarity to an anode for 1 milliamp per centimeter squared for 1 hour to remove the scale. And we had lots of results showing that this actually did help quite a bit. So the results I'm showing here are about 460 hours of continuous treatment. And I'll just highlight kind of the beginning and the end. So over the first 100 hours, we had greater than 99.99% removal of perchlorate. Our selectivity was 100% towards chloride. And in that first 24 hours, I'll highlight that the energy consumption was about zero point 0.5 kilowatt hours per cubic meter. The current efficiency was still relatively low, and that was due to the low concentration of perchlorate. You can see that performance declined over time, and that was related to still calcium carbonate scaling. So we need to do a little bit better job and optimize this reverse polarity treatment, but we're very confident that we can do so. We also monitored the effluent for rhenium and did not detect any. So the catalyst was stable on the electrode surface. So in the final 24 hours, we had 96% removal, still 100% going to chloride, but our energy consumption increased about fourfold and our current efficiency decreased. And we're relating this once again to the scaling on the surface, which needs a little bit more work to optimize. Okay, lastly, I'm going to just briefly talk about the life cycle assessment of our REM strategy versus GAC. This was done for an IMX 101 wastewater, and we collaborated with a DoD base who is using GAC treatment for IMX 101 to get the numbers for GAC. We looked at 10 different environmental impacts, and this is just a comparative analysis. So the way to interpret this is anything, anything above the red line for the REM means that the impacts of the REM are greater than GAC, and anything lower than the red horizontal line means that the REM impacts were lower than GAC. So you can see from the results here that most of the impacts for the REM were higher and GAC had lower environmental impacts. However, this was done very early on for this technology. So it was very useful to see where we could improve. And we saw various ways that we could reduce the environmental impacts. First and foremost, increasing the current efficiency. And we've done lots of work on other projects focused on PFAS oxidation, where we've been able to minimize the oxygen evolution reaction, which is the main side reaction. So we're very confident that those results would apply here as well and to lower our environmental impacts. Also, if we extend our REM life and we recycle the REMs and use renewable energy sources, all of these changes can lower our environmental impacts and put it more competitive with GAC. I want to briefly just show a couple of these here. First off, the figure in the top left is showing the global warming potential for different energy mixes. We utilize this SPSO due to the location where this facility was. However, on the right, we can see if we move to full photovoltaic systems, that would lower the GWP significantly. Also, we also assumed that we were using these electrodes once, and at end of lifetime, we were putting them in a landfill, which is not completely realistic. We would recycle these. So if we assume a 90% recycle of the TiO2 precursor material, I boxed out three of these environmental impacts that are much more favorable for the REM. So these are just a couple of examples of how we can lower the environmental impacts, but ultimately we need to do a complete life cycle assessment with revised data and also look at a cost analysis as well. So I want to wrap up here. I guess overall, uh, what we saw from this work was that the REM system was feasible for oxidation of the munition constituents, all the legacy as well as the IHEs. We looked at this in an IMX 101 as well as an IMX 104 wastewater solution. We also independently look at nitrate and perchlorate removal. What's left to do still is integrating this into a single cell, and we are working on that with other projects. And hopefully, in the future, we can get additional funding and show that can be effective for munitions wastewaters as well. And lastly, the LCA impacts, we've identified many areas where we can improve upon the process and lower the impacts of the REM system and make it more competitive with GAC. So the benefits to DoD, we showed enhanced treatment of munitions wastewater. So we demonstrated that one technology could be applied to removal of all the compounds of interest. Destructive technologies are often favorable because they don't produce any secondary waste, so there's no residual disposal. Electrochemical technologies also are very scalable, so we can easily add additional units and remove additional units depending on the treatment volume needed. And as I mentioned, there are various potentials for lowering our environmental impacts. So with that, I just wanted to thank everyone again for their attention, and I'd be happy to answer questions as time allows.
Thank you so much, Brian. As a reminder to all of you, you can submit questions by using the Q&A box on your screen. We have received several questions that Brian will now answer. And this first question, Brian, has to do with the commercial availability and scalability of the reactive electrochemical membranes. Are these units available or are they custom made? Can you provide the commercialization status of this technology, please?
Yeah, thanks for the question. Yeah, currently we're making all of these in our lab. So the way we make them, they're not commercially available. I think there are some vendors of similar materials. Um, yeah, personally, we're just making these in our lab and we have not started a company on this idea yet. In terms of the scalability, um, we're kind of piggybacking on the membrane technology. And so that's why I provided units such as liters per meter squared per hour, because we always want to operate the system at similar fluxes that you would see for a membrane system. And that allows us to utilize, the scale up factors that membranes have demonstrated and use a similar model for that. So that's kind of our idea for scalability is it should scale if we operate at similar fluxes, just like a ceramic membrane would.
Thank you. And a follow-on question, what is the cost of the membranes relative to, for example, an electrode?
Well, if we compare that to, I mean, we always make the comparison to boron doped diamond because that's kind of considered the state of the art um, for electrochemical oxidation. And we've published some work showing that we can be, 100 to 1,000 times cheaper. But I want to also emphasize that those comparisons are a little bit difficult for something that's, commercially available and has been around a while versus, a new technology. So the costs look good because our main costs are related to TiO2 and hydrogen to reduce them. So we think they can be very competitive and much cheaper than electrodes like boron doped diamond. We just have to demonstrate performance, which we've done here, and also demonstrate longevity, which we've done in our report, our final report for this project as well.
Thanks so much. This next question is from Montclair State University. What was what was the basis for your selection of the TiO407? Why did you select it, and did you look at other materials for use in your reactors?
For this project, I mean, there was a lot of work done before this on other contaminants, and we've worked with this Magnelli phase for some time, and we've investigated, different phases. Ti-407 is the most conductive phase of, the of what's called the Magnelli phases. This is just, fancy word for suboxides of TiO2. So it's the most conductive, and it also produces the highest yield of hydroxyl radicals. So those are the primary reasons that we used it. Also, because TiO2 is the precursor for this, and TiO2 is very abundant and very economical. That was another reason we wanted to look for, economical materials to use for electrodes. But in this project, we only used this. We didn't test others because there's a lot of work done before this that got us to the point that we are now with this electrode.
Thank you. This next question is from Rogers Corporation. Were there any byproducts that were generated? You mentioned that nitrogen was produced during the oxidation step. Was NOx generated in addition to nitrogen, or anything else that you looked for and measured?
Yeah, that's a good question. So we didn't do gas phase analysis. Um, we did, very thorough analysis of the solution phase, and nitrate was the primary product. In some cases, we did detect ammonia, but that was only for NTO. We investigated everything in the solution, and we did not see anything. So I cannot definitively say there was nothing else produced in the gas phase. With the reactions of chlorine and amine groups, there could have been some chloramines that formed and volatilized. Um, yeah, our mass balances were pretty good for the most part. So if there was anything formed, that would be at pretty low concentrations.
Great, thank you. This next question is from the Commonwealth Scientific and Industrial Research Organization in Australia. What is the longevity of the system? In other words, for how long can you run the system, or how much volume of wastewater can you treat before there is a need to replace the electrodes?
Yeah, very good question. So yeah, we did a longevity test as part of this project, and that's available on the sort of website. I don't remember the exact numbers there, but I think we estimated based on we do this what's called a uh, accelerated life test. So we put a much higher current density than you would in operation to try to extrapolate the life, and the life I think came to about 300 days. Um, and we are investigating ways to improve that, and there's things that can be done to improve that. But even at the end of life, what we've seen is that all we need to do is do a regeneration process, and we can reuse them. So the electrodes are not don't need to be disposed of. They need to be reconditioned after some amount of time. But once again, that's based off an accelerated life test, which there may be some uncertainty in that in terms of actual operation.
Great, thank you. And what challenges were encountered during running the system that may impact longevity, just to leverage that longevity question? Anything related to membrane fouling?
Yeah,
When
sure.
you, especially if you manufacture, you use the wastewater that you generated, but what would what issues would you encounter if you used the manufacturing wastewater?
Well, I mean, the biggest challenge that we saw in this project was related to NQ. And we saw that if we did not add sodium chloride, that over time the electrode would foul. And it formed this polymer film. The polymer film actually was conductive, so it didn't seem to affect the conductivity, but it blocked the reactive sites. So that was the biggest problem. We added sodium chloride to remedy that, and that was very effective. But then I guess the question then, I think the biggest question in our minds that we haven't, we haven't addressed is how much sodium chloride do we have to add, and will that create any issues after the fact for disposal? These are very low volumes of wastewater. So even something, as simple as dilution might be applicable for the sodium chloride, but that would be, I say, would be the biggest issue was just related to the NQ. Everything else was fairly easy to oxidize.
Fantastic. And one last question from our Australian colleagues again, before we move on to the next presentation, and we'll come back and answer any remaining questions at the end. But what is the pH of the treated water? Do you have any pH issues?
What was the question? pH?
pH, yes, sir.
After treatment, the pH usually becomes more acidic. However, we were kind of doing this as anode by itself and then cathode by itself, and so I think we can manage that a little bit better by having the downstream cathode to neutralize the pH, because due to water electrolysis, the pH goes down at the anode, but then it also goes back up at the cathode. So I think a final completed electrochemical cell could be designed in a way where the pH does not change that much, but that is also something to definitely to consider in terms of where this water will go after treatment. So yeah, great set of questions.
Yeah, well, thank you, Brian, for doing an outstanding job in answering them. So please stay on. But at this point, we're going to shift gears to our second presenter, who is Dr. Paul Hatzinger. Paul is the director of the Biotechnology Development and Applications Group at Aptim. He has more than 27 years of experience in contaminant biodegradation, bioremediation, and forensics. And his research group has been instrumental in the development of field applications of new in situ and ex situ remedial approaches for a broad range of contaminants, including perchlorate, insensitive and traditional explosives, 1,2-dibromoethane, and NDMA, and 1,4-dioxane. Paul has authored more than 100 peer-reviewed papers and book chapters, and has served as PI on research grants from NSF, EPA, DOE, AFCAC, Navy, Army Corps of Engineers, in addition to SERDP and ESTCP. And finally, he earned his doctoral degree in environmental toxicology from Cornell University. Paul, please go ahead.
Great. Thank you, Rula. Thanks, everybody. I'm going to switch gears a little bit from Brian's talk and talk about treating these same type of wastewaters, but with a bioreactor system. Oops. So a little bit about the outline. Brian did a great job sort of laying out the problem statement. So I'll talk about our objectives, a little bit of background about biological treatment, and then we'll go through some of the results, how we develop cultures, operation of this membrane bioreactor system. I'll touch on a bit of cost analysis, and then look at conclusions and some of the benefits to DoD. Okay, so our objective was to optimize a resilient treatment train for these mixed energetic wastewaters. So kind of the same issue or statement of need that Brian responded to. But one of the things that we were interested in is trying an anaerobic membrane bioreactor, because we knew this bioreactor design had not been used for these complex wastewaters in the past, and it seemed like a very good fit. But we also understood that we were probably going to need a secondary process, which could be an aerobic MBR or electrocatalytic treatment, maybe UV AOP, or just a simple bleach system. So those are the types of things that we were looking at to treat this complex wastewater system. Okay, so a little bit of background on explosives biodegradation. Most of these munitions constituents are subject to anaerobic biodegradation. This includes the traditional compounds like RDH, HMX, and TNT, as well as these IHEs. Also, things like perchlorate and nitrate. So one of the things we know was that, For some of these things like perchlorate and nitrate, we understand the organisms and the pathways of breakdown. But for some of these other explosives, things like NTO, this can be a little more complex. And we know there's usually nitroreductase enzymes involved, but when you're reducing compounds like this can be co-metabolic, so the organisms don't gain much from it. They can use these compounds as electron acceptors or sometimes nitrogen sources. But also, you may need multiple organisms or slightly different reduction conditions in order to completely degrade these. And one example is NTO, which will often go anaerobically to ATO and then aerobically through to CO2 and ammonia. So the redox conditions here can be very, very important. Okay, so for the membrane bioreactor, this is a suspended growth system. So bacteria will actually grow in suspension in a vessel, and you get bacterial degraders that will sort of grow up there. So you would feed in your wastewater, bacteria grow and degrade those compounds, and then you have one or more membranes that can be internal or external. And the bacteria can't pass through the pores of the membrane, but you get effluent that can. So your effluent or permeate passes through. The nice thing is you can maintain a diverse population. You don't get washout like you do in some type of systems because of the membrane. So if you're switching explosives from one type to another, you're not going to have to worry about maybe those organisms washing out. You also get a very high quality permeate. The third thing is this is a very scalable system and there are commercial units available. So you can order MBRs of many different sizes. So this is directly scalable right now to a full-scale system. So again, I mentioned secondary treatment. We knew an anaerobic MBR was not going to treat all of this, in part because when you get reduction of some of these compounds, you can get intermediates like DNAN going to 2-anan, NTO to ATO, as I mentioned before, and RDX can have some other intermediates, and these can be persistent. And you also have to think about things like ammonia, methane, hydrogen sulfide, as this is an anaerobic process, as well as TOC and color. So again, we looked at a secondary treatment phase, and I know you're excited to know what it was. And I'm going to tell you right now that what we did is we did a dual anaerobic aerobic membrane bioreactor, and then we did a little bit of polishing at the end with bleach, although we tried some of these other oxidative technologies as well. So to start with, then we had to develop an inoculum. So basically, we started out with kegs, and we seeded these with a variety of different materials, including some sediments from explosives contaminated wastewaters. We inoculated them also with some material from an operating methanogenic fluid bed reactor, as well as some pure cultures. And we looked at, in a series of these kegs, different types of carbon sources, different redox conditions. And then when we got one environment where we said, okay, we're getting a lot of good degradation, we started to sort of scale up. So we went from a keg to a 7-liter reactor, from the 7-liter to a 20-liter reactor, and then from that, we seeded the MBR. And these are just some results from the 7-liter reactor. And this was a system that was fed fructose, cheese whey, and a little bit of yeast extract. And those small amounts of cheese whey and yeast extract really help stimulate the activity of some of these organisms for one reason or another. It might be vitamins or cofactors that are included. But here we see degradation again in this batch 7-liter system of many of these contaminants, TNT, NTO, DNAN, RDX somewhat more slowly, and then also perchlorate. So we knew we had a pretty good inoculum for the reactor. And this is what this reactor looks like. These were big systems. The dual MBR system, this is just showing what the anaerobic system would look like. We had an influent reservoir, our fructose, yeast extract, and cheese whey feed, a little bit of base because you get some acidification during the process. And then we had a reactor unit that held about 50 liters with an internal membrane. There's a level sensor that basically will keep this at a certain level, and the feed goes automatically to the aerobic MBR. We have an ORP probe, and then a mixing system to keep the system well mixed. Now the aerobic MBR looks just like this, except that it has an acid feed system to control pH, and an air pump, so to keep everything aerobic. So these are set up in sequence. And here's a photograph. So this is our pilot plant. Here's the anaerobic MBR sort of in front of us. There's the aerobic MBR in the background, sort of a sampling table and carbon feed tank, and then the influent tank, which was basically a beer keg, so you can keep things anaerobic, where we would add our feed water. Now, when we started out, I'm going to talk about what we had, we call our standard mix, which included all of these different traditional explosives, RDX, HMX, TNT, as well as the IHEs and nitrate and perchlorate. And we had sort of plus or minus ammonia. We had about a 4-day HRT, or hydraulic residence time, in the system. And our substrate feed was fructose, again, a little bit of yeast extract, a little bit of cheese whey. Now, as we move along, and the nice thing is here also is we operated this system for almost 2.5 years. So see 883 days of continuous operation. So the system was very resilient, and that was with basically no downtime. So just in terms of these sequences, as I show you data, I'll kind of point out what we did here. You know, we started out with kind of our full mixture minus ammonia, and then or plus ammonia, then we took ammonia out. We added perchlorate from 10 to 100 milligrams per liter in this phase from day 120 to 169. And then we shut the flow down altogether and just mixed the system. So trying to see what would happen if you had a major, if you had a major failure or a pump failure or shutdown in the system for a couple of weeks. We did an IMX 101 simulation where we removed everything but DNAN, NTO, and NQ. And we went back to standard conditions again. And one of the things we were trying to do is understand if we pull out things, we pull out TNT and RDX for a long period of time, a couple of months. When we add it back to the system, are we going to have a long lag period, or are we going to see sort of the TNT and these other things start breaking down again very, very quickly? Because that's important for, real world operation. We switched over to a cheaper sugar source at one point. We tested hydraulic residence times to sort of optimize. And then we used the same IMX 104 washdown water that Brian talked about in his system. And we did this in dilutions, 1/100 strength. And that's just because the NTO in this water was so high that it was crystallizing out. So it was at saturation. And then we tried again at 1/10 strength. So that just kind of runs through the way we operated the system. Okay. Apologize there. I'm kind of frozen up here, I think.
We can go ahead and advance the slides for you, Paul.
Okay, that would be great, Rula. Thank you. Could we go to slide 48, please? Okay, so I'm going to show you data here, and we're going to start with the anaerobic MBR. And basically on the right-hand side, I have the structures of the compounds we're talking about, and I'll show you whether it's the anaerobic or aerobic MBR. On the top here, this is all the sequence that I just showed you in terms of what we were feeding, in this case, fructose, and then we switched to a cheaper invert sugar and all of the different sequences that we ran through. And the good news here was for treatment of perchlorate and nitrate, we essentially had no breakthrough at all. And I will say what I'm not showing here is when we started this reactor up, before we seeded any cultures, we fed these materials through to make sure our influent and effluent from both reactors were pretty much equivalent. So we're not looking at sorption or any other kind of losses here. So the system beautifully treated both perchlorate and nitrate with no issues all the way through. And even when those were taken out for long periods of time, there was basically instantaneous recovery of activity, which was great. Okay, so next slide, please. Okay, so with TNT, we had very, very similar results. Again, we fed this in at several ppm. When we put in the IMX 101, we saw basically no TNT here for a while, but we had instantaneous removal again. And we looked for all of the potential daughter products, the partial reduction products for TNT. And basically we saw, that there was none of them produced. So we're completely degrading TNT in this case. So can we go to slide 50, please? So for RDX, we did see a little bit of RDX breakthrough early on, and particularly when we bumped the perchlorate, I think we got a little limited in carbon source. So we do see a little bit of breakthrough of RDX here from day 100 to 200. And then a couple of bumps again when we started to reduce the HRT. For the most part, we had more than 99% treatment, but we did see a little bit of breakthrough. So now I'm going to switch over on slide 51 to show you the aerobic MBR, because of course, all of the permeate from the anaerobic system is going to the aerobic system. So in blue, we see the influent, and notice the scale is different. So we're only up to about a half a ppm here. And we see that we're getting complete removal here early on, and we get a little bump with the high perchlorate in the system. But aerobically, we're getting a very good polishing treatment of the RDX overall. You can see we're down here in the 50 ppb range at a maximum or a little bit below that. And our detection limit, our PQL here was about 20 ppb. So if we could go to slide 52, please. Okay, for DNAN, kind of the same story, that we had very, very good removal of DNAN throughout the entire operational period of the reactor. And this was a little different than our batch system. In our batch system, we had buildup of 2-anan, and it kind of became a terminal product. So that may be the result of the fact that in the batch type system, you're not getting any different nutrients or vitamins. You're sort of just doing this in batch, and bacteria can start to run out of things that they need. Whereas in the flow through system, apparently that worked much, much better. We saw a little bit of 2-anan early on, but then it was non-detect throughout the rest of the process. So slide 53. Now, nitroguanidine is sort of another character, and Brian had difficulties with nitroguanidine, as did we. And early on, we were seeing basically, a little bit of removal and then virtually none as we're going through our different phases, 15 or 20%. And then magically, without us doing much of anything, when we're running through the standard mix about a year into the process, we suddenly started seeing very significant reductions in nitroguanidine. And I believe what happened here is we just, this community is evolving, and something evolved in there. And this could have been, God knows where this organism came from or what happened, but suddenly we're starting to see reduction. And I assume this is a microbial population or an organism that is using nitroguanidine in some way anaerobically. No one's ever isolated a bacterium that can do this, but there is some precedent in the literature. There was a relatively recent paper showing some losses under sulfate reducing conditions, and there's some older literature on anaerobic losses of nitroguanidine. But again, this was pretty interesting, and you can see where we're getting well over 90% removal once this process started, irrespective of the different changes that we made, and even after removing it from the system for a while. So if we could go to next slide, please. 15. Okay, so switching over to the aerobic system. So when we're getting a lot of breakthrough early on, we weren't getting much aerobic removal. And then we started to see a bit of removal, and we had an enrichment culture that we added to the system. And that was actually taken from the aerobic MBR and enriched and then added back. And then we saw some nice removal, but it sort of fell off a little bit. And again, later on, when we started seeing very good anaerobic removal, the polishing in the aerobic system was nearly 100%. So basically, we were getting little to no breakthrough of nitroguanidine after a period of time. And as we looked further, we realized, there's not much known about nitroguanidine degradation. So if we go to slide 55. So one of our collaborators on this from Texas A&M is Bella Chu, and she had some students who became interested in this. And we sent her our NQ5 enrichment culture from the reactor. And they also took some other materials from a landfill and from Galveston Bay sediment. And they started trying to see if they could get something to grow on nitroguanidine. And here's the structure of this compound. You can see it's very nitrogen rich, but only has a single carbon. They couldn't get any organisms to grow on this aerobically or anaerobically, but they found if they added glucose And only this compound is a nitrogen source. They started to get organisms that grew, and they purified some cultures. And the one that they purified from the aerobic MBR, so this NQ5 culture, was Pseudomonas extreme australis. And this organism, then they did some additional studies in the lab. They found that it rapidly uses nitroguanidine as a nitrogen source. It prefers ammonia to nitroguanidine, but nitroguanidine to nitrate. This may have to do with oxidation state. And we published a paper on this last year, and I'd be happy to send you that paper if you have more interest in this microbiology, because it was really pretty interesting. Slide 56. Okay, so to finish up, the other sort of troublemaker in this reactor was NTO, and we didn't have a lot of trouble getting rid of NTO itself, but we had a lot of trouble with the ATO, and that's the first reduction product. So this nitro group goes to an amine, and the ATO was relatively persistent. This has been shown in the literature, so this is not unexpected. Typically, ATO will go aerobically after NTO goes anaerobically, and Jim Field has done a lot of work on this. We were very excited early on because the ATO was not forming, and then slowly it started to come, and then we sort of had an equal amounts, and then ultimately anaerobically we were getting rid of about 40% of it. So there was some anaerobic loss of ATO in this system, which was interesting. We don't know which organisms potentially were doing this, but we were still getting, breakthrough of the ATO. So next slide, please. In the aerobic reactor, we really weren't seeing any loss of ATO. So, when our influent and our effluent were pretty similar, and I'm basically showing you here the first about 400 days of operation, and I'll split out in a second, I'll talk about basically when we added the actual IMX 104 water, which has a lot of ATO. So slide 58. And you can see when we added 1/100th strength wastewater in the anaerobic system, again, we're converting all of the NTO, and most of it's going to ATO minus about 10%. And again, when we go to 110 strength wastewater, you can see we're up around 2,000 ppm of NTO entering the system. It's all being biotransformed, but again, we have ATO minus about 40%. So we do have an ATO as a terminal product that we had to figure out a way to deal with, and that was really the one product that was being produced that was going through the aerobic reactor. So we were getting very, very good treatment overall. Slide 59. And again, just showing aerobically the ATO is passing through. So we did inoculate a culture that Jim Field sent, and alas, within this system with these high concentrations, it didn't seem to take off. Now, there was some evidence in the red circles that we were getting some aerobic losses sort of later on, but throughout most of the course of this, ATO, as you can see here, was a persistent product through the reactor. Next slide. So we looked at some more complex things. We looked at UV, AOP, we looked at electrochemical oxidation, but it turned out that this ATO was pretty readily oxidized just with a relatively dilute bleach solution. So basically a system where you have the anaerobic MBR, the aerobic MBR, and then bleach turned out to remove all of the ATO, and that was the last sort of daughter product that we had within the system. It also did a very good job of reducing the color from sort of a dilute root beer to relatively clear permeate. So, ultimately we get rid of all of those materials with a little bit of hypochlorite. Slide 61. Now, when we went to the IMX 104 wastewater and you have a lot of ATO, this still worked fine, just had to increase the hypochlorite solution to about 5% from 0.1%. But once again, with this real wastewater, you're removing everything, including the ATO. And so you have, some residual ammonia, but when you go through the aerobic system, a lot of that is taken care of. So this worked very, very well. Slide 62, please. And I'll mention also that a cost analysis was done, and this was done by Todd Webster of Environment Technologies, who's got a very good background because this company actually sells membrane bioreactors and fluid beds and other reactors. So he did a full cost analysis to put together a system, and he did sort of a Cadillac that would basically be a system that could operate at 10 GPM 24/7. That's probably a much larger system than someone would need. But looking at both costs for the equipment as well as operational costs, and ultimately you end up in the cents per gallon range in terms of capital and operational costs at a 10 GPM type of system. Slide 63. So just to finish up then, the system proved to be highly effective for this large mix of materials. It was very resilient to upsets and changing mixtures. ATO is a residual, but bleach takes care of that. And that's also nice too, because you kill if there's any residual bacteria in the material. And it did a pretty good job of treating this washdown water, at least at 1/10 and 1/100 strength. Slide 64. So benefits to DoD, this is a nice resilient system. And the nice thing also is you can switch from different types of wastewaters. We showed here that this system, the bacteria are maintained. So even if TNT is not in this system for a period of months, it degraded very, very quickly, very readily. So you can see those sort of mixtures and differing mixtures being treatable here. And it's commercially available right now. So you could actually order one of these. Slide 65. I'd like to acknowledge a lot of folks who worked on this. This was a very good team of university folks as well as government and different companies. Texas A&M did a lot of work. Todd Webster, Environment Technologies. Pam Sheehan at Picatinny Arsenal was a contributor, as well as Charles Schaefer at CDM Smith. 66, slide 66, please. And so thank you very much. If you want information or to talk about this, please give me a call or shoot me an email, and please visit the project site to look at the different papers, and the final report should be posted soon. So thank you very much.
Great. Thank you so much, Paul. We've received a number of questions. The first one is from BAE Systems. Do you believe that this process would be effective for processing wastewater contaminated with DNT, dinitrotoluene?
Yeah, good question. I would with something like DNT. I'm trying to recall whether DNT goes aerobically or anoxically. I would have to look that up. I think a membrane bioreactor would be an excellent option, but we'd probably, it's something you would want to do a pilot study, take a look back at the microbiology, and it may be that you wouldn't need a dual system if that was your main contaminant of concern, just potentially an aerobic or anaerobic. But off the top of my head, I don't remember whether DNT prefers to go aerobically or anaerobically.
Great. Thank you, Paul. This next question is from the University of Delaware. Why is ATO a concern, and how do we know that chlorination products of ATO would be acceptable?
Yep. Yeah, very good question. Well, it's not a regulated compound, but like anything, when we're treating these materials, it's best if we don't have daughter products coming through, which is why our ultimate goal was to remove all of the explosives and all of those daughter products. The oxidation reaction of ATO, my assumption is that it breaks the ring. We didn't see anything that we could detect by HPLC that was a daughter product in that case. My assumption is that we're probably breaking it down to some smaller aerobically degradable compounds that are going to be small carbon nitrogen compounds and or ammonia. We did see some significant increases in ammonia, so that's probably you're probably getting close to a mineralization of that compound, but if we weren't getting a ring cleavage, I think we would have seen that by the HPLC method as an unidentified peak, which we did not see. And there was nothing else that showed up in our analytical that would have been a small daughter product that we could actually measure. So it's basically just the stewardship of removing all of these compounds from the wastewater so that it can be safely released.
Great, thank you so much. This next question is from the Commonwealth Scientific and Industrial Research Organization in Australia. For the anaerobic MBR process, was 2.2 days the lowest hydraulic residence time tested? And have you looked into reducing the HRT further than that?
Yeah, really good question. That was as low as we went. Part of that was just the fact that we had to make up a lot of this wastewater, and you start to get where you're for 50-liter reactors, you're using some pretty large volumes of materials and explosives when you're doing that. The second part was we were sort of reaching a point. We were about a year and a half in at that point when we started with the HRT, where it was time to probably scrub the membranes for an automated system that would be built in where there's a sparging system to clean membranes, but our membranes weren't, they didn't have the permeability they had earlier. So we didn't want to push that any farther for those two reasons. But I think if one were looking at a commercial system, you might be able to reduce that a little bit further, particularly after it's operated for a period of time. And of course, there's going to be a cost savings associated with that in terms of sizing of reactors and that. So that's a very good, insightful question. We didn't go any further than 2.2 days.
Thank you. And a follow-on question also from Australia. What was the biomass concentration that was maintained throughout the process? And was there a need to waste any biomass?
Yeah, another really good question. Someone who knows something about reactors. So we never wasted biomass. In a commercial system, you would likely do that, but the concentrations. And I will say too that we studied the microbiology of this system, so it's very complex, and there's a lot of different organisms. In the old days, you would look for organisms that you wanted to find, and you hope to find there. Now you do next generation sequencing, and you find everything, and then you spend a whole lot of time trying to figure out what all these different bacteria are doing there. But off the top of my head, I don't recall what we did measure. We did measure the OD. Off the top of my head, I don't have a number. It of course it was relatively high, but I can't remember. I'd have to pop back and look through the paper, but I'm happy to send you we published a couple of papers on this at this point.
Great, thank you, Paul. Did you track parameters like methane and hydrogen sulfide in the dual MBR system?
We did. We tracked all of those different parameters. We tracked, COD, TOC, methane, ammonia, hydrogen sulfide, and for the most part, the aerobic reactor did an excellent job of removing those materials. So there was very little methane. There's methane and hydrogen sulfide coming from the anaerobic reactor to the aerobic, because we were operating at an ORP in the -300 to -400 range. So you're going to expect to see some of those materials, but they were pretty much removed in the aerobic system. Most of the ammonia was removed, and we did add a nitrifying culture at one point throughout most of the system, where we started to see, and again, with things like BOD, we got a 90+% reduction in BOD going again through the aerobic reactor. So that was a very important step in getting rid of all of those materials. The only time where we saw buildup of anything that you might be concerned about is when we ran that super high concentration of NTO in the IMX 104 wastewater, and we got about 75 ppm of ammonia. in the aerobic system coming out. But again, we were treating at that point, a good deal of NTO down to ATO, and again, about 40% of the ATO. So presumably that ammonia was either from biomass or was from the anaerobic breakdown of the ATO during that phase. But most of the other parameters actually look very good coming out. And it's certainly, you could release it to a wastewater treatment plant without issue.
Fantastic. And one last question before we pull Brian back in. When you do get to a full-scale system, do you expect any issues with membrane biofouling?
Yeah, that could happen with time, but the full-scale systems are designed with a scrubbing unit. So it can be a air or nitrogen sparge or other types of systems. So you can clean those membranes internally, and some of the full-scale MBRs would have an external membrane, so it's not within the tank like the ones that we use. But that would be automated, so you can do a back flush of that membrane and should not have to, should have a very, very long life for those membranes without a fouling consideration.
Great. Thank you, Paul, for a great presentation and really great responses to the questions. We're going to go ahead and pull Brian back in. I'm going to ask you both the same question, which is to sort of elaborate about the next steps in your work in terms of scaling up and any sort of field demonstrations. So that you perhaps may be thinking about. Brian, can you take a first crack at this question, please?
Yeah, sure. Yeah, good question. Yeah, currently, our funding for at least the munitions wastewater project has ended. I guess there's opportunity for ESTCP. Um, but we see this technology as kind of a platform technology. So we've applied it to many other types of contaminants. Right now, a lot of our funded work is focused on PFAS. And so we are working hard on scaling that system up on various projects within startup and external to startup. Um, but there's no pilot plant projects that we have currently funded. But like I said, there is the opportunity to apply to ESTCP, and we're also always searching for other availability of funds.
Thank you, Brian. Paul?
Yeah, so for a SERDP project, we ran some pretty large scale reactors already. So again, these were 50-liter units, so they're really of a pilot scale. So I would say, Rula, that this technology could be applied now. So I think we have the information. You would probably run a small scale pilot if you have a specific waste stream. For instance, the DNT was mentioned. So just to make sure that the treatment would be appropriate and you could do it within the residence times. But these type of reactors now, although they're custom designed, you can get them at any sort of scale that you need. So and I just mentioned a partner on this was Todd Webster at Envirogen Technologies. They sell these type of reactors, as do some other vendors. So I think we've shown this at a scale that is appropriate for the next step, which would be full-scale application in the field. We could certainly, even with these larger reactors, do a pilot at an actual site where you have a wastewater. Again, that would be another step before the full scale, just as a proof of concept if the wastewater differs substantially from the types of things that we tested here. But I feel this technology is ready to go.
Thanks so much to both of you. We had one more question squeeze in for you, Paul. What was the temperature that you operated at for the biological portion of this?
Yeah, it was 24 plus or minus 1.9 degrees Celsius. And I know that because I saw the question come up and I peeked into the manuscript.
All right.
But it
Well,
was it was indoors, but it did get a bit cooler in the winter. It's not a room that's super well heated, so a little cooler in the winter, a little warmer in the summer. But that was the average overall.
excellent. Well, thank you again both for a fantastic webinar. And we're going to go ahead and wrap up. But we'd like to remind you to please visit the SERDP and ESTCP webinar webpage to register for upcoming webinar. Like Andrea said, we do archive all past webinars. So if you'd like to refer to this webinar, it should be uploaded over the next week. The PDF of the slides is available for download now, and the video will be available as early as next week. So please make sure to visit the webinar webpage to access all of the webinar materials. And we would appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for joining us.